So, welcome to today class of nonlinear vibration. So, we will start a new module today. So, that is on stability and bifurcation analysis of nonlinear responses. So, in this module, we will have 6 classes. So, first 3 classes we will devote to the stability and bifurcation of fixed point response. So, there we will study about the static bifurcations. So, in which I will tell you about this pitchfork, saddle node, transcritical bifurcation, then about the dynamic bifurcation, that is Hopf bifurcation. And next 2 classes we will study stability and bifurcation analysis of these periodic responses. So, here we will study about this monodromy matrix, we will also study Foucault theory and Lyapunov exponents. So, then we will study about this quasi periodic and chaotic response, and in this module in the last class I will tell about different routes to chaotic responses. For example, these will be period doubling route to chaos, this torus breakdown route to chaos, then intermittency, and also we will discuss about this crisis. Also some methods to control this chaotic response and the usefulness of this chaotic response also we will discuss in that class. So, coming to the stability and bifurcation analysis, first we should know what we mean by stability of a system. So, previous classes we have discussed or we know different type of nonlinear systems. So, particularly we have studied about this Duffing equation. So, in which we have taken the system in this form, that is x double dot plus omega n square x plus 2 zeta omega n x dot plus alpha x q. So, if you are taking cubic nonlinearity, otherwise we have this both quadratic and cubic. So, in case of quadratic we are adding a quadratic term, that is alpha 1 x square we can add. So, either this can be 0. So, we can put this side 0 for free vibration, or we can put this forcing term, that is epsilon f cos omega t, to find the forced response of the system. Actually, we are going to study in detail about this Duffing equation or other type of equation in our applications, and in the previous module we have discussed about different solution methods, how to solve these equations. So, in most of the cases we reduce the second order differential equation to a set of first order differential equation, and we obtain the steady state response by eliminating the terms which does not depends on time. So, we have studied this Duffing, or we know these different types of equations, that is Duffing equation. Then we also know about this van der Pol equation. So, in case of this van der Pol equation, the equation is in this type, that is x double dot plus x equal to mu into 1 minus x square into x dot. Also we know these parametrically excited system equations of parametrically excited system, in which a time varying term is the coefficient of the response. So, for example, in case of Hill's equation we have the equation x double dot plus p t x equal to 0, when this p t, that is periodic time, takes the form delta plus 2 epsilon cos 2 t, then we tells this Matthew equation. So, in general now we are acquainted about these 5 different types of or 4 different types of equations. Also, in addition to that, we know these equation in their force vibration form or free vibration form, and in these equations we know different methods to solve them. First, we use this qualitative analysis method, in which we use both potential energy and kinetic energy terms and equating, or by finding the potential well or finding the potential energy or variation of the potential energy. So, we found different types of response. So, corresponding to, for example, corresponding to the maximum potential energy, we have this saddle point, and corresponding to this minimum potential energy we have the center, and here also corresponding to this maximum potential energy we have this saddle point. So, this is shown the potential. So, this is the variation of the potential energy, and these other curves show the flow of the response. So, one can obtain or one can perform the qualitative analysis to find the different types of response of the system. So, these response, that is what is written S, C and S or the center, saddle point. So, these responses are the fixed point response of the system. So, one can obtain the fixed point response of the system by neglecting or by putting the time varying terms to be 0. Also, in addition to the fixed point response, so we can have this periodic response. The response may be quasi periodic or the response may be chaotic. So, we have mainly 4 different type of response. So, first one is the fixed point response. Second one, we have a periodically varying system or periodic response. Third one, we have this quasi periodic response, and finally, we have this chaotic response. In case of fixed point response also, so we can have a trivial response or non-trivial response. So, for example, so in this equation x double dot minus x equal to 0. So, let us take this equation. So, in this case, so the solution, so if we put this x double dot equal to 0. So, we can find this x equal to 0 is the equilibrium point. So, corresponding to this x equal to 0. So, if we find what will be the response of the system, one can see that the system response may grow at this point or the system may be unstable. So, first we should understand what we mean by the stability of a system, what is a stable system, what is unstable system. Then we can perform the analysis or we can discuss their types of stability and types of bifurcation in the system. So, previously we have studied all these methods, that is straightforward expansion method. After qualitative analysis, these are this quantitative analysis we performed. So, here we have used some perturbation technique. So, in these cases we have studied the straightforward expansion, then Lindstedt Poincare method, then harmonic balance method, method of averaging, method of multiple scale, incremental harmonic balance method, intrinsic multiple scale harmonic balance method, or this multiple time scale harmonic balance method and modified Lindstedt Poincare method. So, in all these cases or in most of the cases except this harmonic balance method, so we reduced our second order differential equation to a set of first order differential equation, and by solving those equations we obtain the steady state response of the system. So, in those steady state response, so now we should know what we mean by a stable response or what we mean by an unstable response. For example, take the simple spring mass damper system, a linear system. So, in this linear system or simple spring and mass. So, if you take simple spring and mass system, instead of taking damper, the system will be very simple. So, the equation already we know. So, this is m x double dot plus k x equal to 0. So, in this case, so this x double dot plus k by m. So, if I write omega n square x, so this is equal to 0, and the solution we know. So, the solution becomes a sin omega t plus phi. So, where we can obtain this a and phi from the initial condition. So, if I plot this x versus time, so we can observe that the response is bounded. So, we have a sine curve. So, the response is bounded. So, if there is damping in the system, then if in case of a, so if there is damping and in case of the underdamped system, so we know the system response can be represented like this. So, it will decay and finally, it becomes 0. So, in this case the system response becomes bounded. So, this is in this case as it comes to the 0 response or trivial response. So, we can tell this is trivial response when the response becomes 0, and if it has certain magnitude or amplitude of vibration, then we can tell that response to be non-trivial. So, in this case what we observed that the response is stable, that means it is bounded. So, we can have a bounded value of the response, but instead of taking this m x double dot plus k x. So, if I will have a value of minus k, that means, so if I will take the system in this way, that is minus x if I will take. So, in this case this x double dot minus omega n square x. So, minus omega n square x will be equal to 0, and we will have a. So, in this case the auxiliary equation becomes d square minus omega n square x equal to 0, or the roots becomes. So, our d will becomes omega n square, or d will be d square becomes omega n square, or d equal to plus minus omega n. So, the solution becomes, so x will be equal to C 1 e to the power omega n t plus C 1 e to the power minus omega n t. So, in this case, so this part, that is C 2 e to the power omega n t. So, with t tends to infinity. So, this part tends to 0, but this part, that is C 1 e to the power omega n t, with increase in t. So, the response exponentially this response will grow. So, if one plot the phase portrait, in this case phase portrait, that means if you can plot this x versus x dot term. So, starting from this, so starting from a very small initial condition. So, with time, so one can see that this response will grow. That means, so if we perturb from the initial condition, that means if we start from a initial condition this, then in this case a system with negative damping in negative stiffness. So, in this case the system response will grow, and with time it will be very large. So, there will be large amplitude of vibration, or the system may become unstable. So, by a stable system we mean that our response amplitude will be bounded or within certain limit, and in case of unstable system, so we can observe that the system response grows and it becomes more and more with time. So, that means it is not bounded. So, if we are not getting a bounded solution, so the system becomes unstable, and if we have a bounded solution, then the system is stable. So, this is the simplest way one can understand what we mean by stability of a system. That means, if we have a bounded system, bounded response, then our system is stable, and if we have a unbounded solution, then the system becomes unstable. So, for studying the stability of the systems, there are several methods. So, let us first see different responses of the system. For example, in case of the Duffing equation. So, in case of the Duffing equation with damping. So, let us consider the Duffing equation with damping, that is, if you will take the equation in this form, u double dot plus omega n square omega 0 square u plus 2 mu or 2 epsilon mu u dot plus alpha u cube equal to 0. So, if you take this equation, so already we know the frequency amplitude relation in this case. So, unlike the linear system, so in case of the linear system, that means if you put this alpha u cube, so this nonlinear term equal to 0. So, already we know in case of the linear system, the response, the steady state response of the free vibration will tends to 0. So, if this mu, that is the damping term, is very small, that is if we have underdamped system. So, in case of underdamped system, we will have a oscillatory motion, and but finally, the response will slow down to 0. But in case of this nonlinear system. So, we already obtain one frequency amplitude relation. So, where sigma represent the detuning parameter and this is the amplitude. So, the amplitude depends on the frequency of the system. So, with change in frequency of the systems, we have observed that the amplitude of the system also changes. So, this figure shows the amplitude and detuning parameter. So, for different value of alpha. So, for alpha equal to plus and minus. So, this is for plus 10 and this is for minus 10. So, alpha corresponding to plus value. So, this the system becomes or the system contains a hardening type of spring or hardening type of spring, and in case of alpha equal to negative, one can have a softening type of spring. So, physically this alpha positive represent a hard spring and alpha negative represent a soft spring, and in this case the response curve will becomes like this. So, this becomes alpha equal to 0, that is for a linear system, and alpha equal to plus 5. So, this is for this nonlinear system, and with increasing nonlinearity we have this different type of response. So, after getting this response curve, so we can one will be interested to know. So, what will happen to the system. So, if it is in the frequency, if it is working or the working frequency, let us take the working frequency corresponding to detuning parameter this. So, corresponding to detuning parameter this. So, what we have observed that we have this is one solution, this is the second solution and this is the third solution. Unlike in case of the linear system. So, for each and every frequency we have a single value of amplitude. In this case we have multi solution. So, due to the presence of this multiple solution, we should know actually at what will be the system response at that frequency. So, it depends actually on the initial conditions what we have taken. So, depending on the initial conditions, so either it will have this value or this value or this value, and whether these responses are stable or unstable. So, one should study, and then depending on the stable or unstable solution. So, one can tells that in which state the system response will be there. So, to study these stability of the system, so we can take these points at the equilibrium points and perturb about these points to know whether the system response is growing or whether the response becomes bounded. So, if the system response grows, then in that case, so we have a unstable system, and if the system response becomes bounded, then we can have a stable system. So, if the response amplitude becomes 0, so for example, we can have a 0 amplitude. So, if the system response becomes 0, then this will be trivial state, otherwise this will be non-trivial state. So, in case of the trivial state, the system response becomes 0, and in case of non-trivial state, the system response we have definite amplitude of system response. Both for the trivial state and for the non-trivial state, one should find the stability of the system. So, this curve shows only the response. So, one can do further analysis to find whether the response is stable or unstable. As we have changed this alpha value and we obtain different types of response, similarly one can change the value of damping, or by changing the value of damping one can find different response. For example, in case of damping equal to damping parameter mu equal to 0.01. So, this is the curve, and with increase in damping one can see the response amplitude decreases. So, in this case let us assume that this part of the response is unstable. So, which we can later we will verify that whether it is unstable or stable, but for the time being let us assume that this part of the response is unstable. So, in this case with increase in this detuning parameter or with increase in this frequency, so starting the system response at this point, so the system response will grow with increase in frequency, and so it will attain a maximum value here, after which further increase in this frequency will bring the system response down. That means, we will have a jump down phenomena here. So, already in the module 1, so we know different types of phenomena associated with this nonlinear system. So, this becomes, or the system response become. So, system response from this point, it will jump down to the system other type of response. So, now if we sweep down the frequency, let us start at this frequency. If we sweep down, then it will follow this path, this will follow this path up to this position, and at this position, as this branch is okay. So, at this position with further increase in frequency, so it will jump up to this position, and with further increase in frequency, it will follow this path. So, it will follow this path with further increase in frequency. So, if we sweep up the frequency, then it goes on increasing, and finally, it jump down to this response, and it jump down to that response, and again with decrease in or sweeping down the frequency at this point. So, it becomes, it moves up or jump up. So, this phenomena is the jump up phenomena. So, it jump up to this response, and further decrease in frequency, it will move or follow this path. So, in this case, so this branch, so we have assumed this branch to be unstable, that means the system will never attain this response. So, either the response, if this part and this part are stable, so either the system will have a stable response here, and corresponding to this point it will have a unstable response. So, depending on the type of response. So, here what we observe, that further increase in this position. So, it get jump down, and after this we have only one solution, and up to this, okay, so up to this point, so we have a single solution, and after this point we have, so we have seen that we have 3 solutions, but out of which 2 solutions are stable. So, we can tell up to this the system is a single stable state. After this, it has a bistable region, or the system has 2 stable region and 1 unstable region. So, system has a bistable region. In many cases also the system may have multiple stable region, and depending on the initial condition, so we can tell to which state the system can go. So, at this point, so this is a critical point, after which, so this point is a critical point. So, after which we have multiple solution. Up to this we have only single solution, and here we have change in this number of the solution. So, this point where the nature or the number of the response of the system changes. So, those points are known as bifurcation point. So, this point, at this point we have a bifurcation point. This means that at this critical frequency or after this critical frequency, the nature of the solution or nature of the response of the system changes, or we have the number of solutions of the system changes. So, here also, so this will be a critical point. So, after which we have only a single solution. So, up to this we have multiple solutions, and after this frequency we have single solution. So, in this way we know, so at bifurcation point either the stability of the system changes or the number of solutions or the number of responses changes. So, either qualitatively or quantitatively the stability and of the response changes at bifurcation points. So, similarly, so one can change different value of this k and one can find the response. So, those things we will study in detail. So, this is a forced equation, that is the equation force dropping equation is in the form. So, u double dot plus omega 0 square u plus epsilon alpha u q equal to epsilon k cos omega t. So, in this case by changing this amplitude of the response also one can get different type of response. So, after getting the response, so one can study the stability of these responses. So, these responses what we obtain by putting this or finding the steady state response. So, these response, so either it has a fixed 0 value or it has a fixed non trivial value. So, these point, that means the system will have certain definite amplitude of excitation. So, if the amplitude of excitation is fixed, then we can tell the response to be a fixed point response. So, in addition to this fixed point response, so in most of the cases we have this periodic response. So, for example, in case of the spring mass system m x double dot plus k x plus c x dot equal to f cos omega t. So, in this case we have a periodic response. So, if we plot the phase portrait of the response, that is x versus x dot, then we have a closed curve for this periodic response. So, now if we increase, let us instead of taking this f cos omega t, so let us take two frequency. So, m x double dot plus k x plus c x dot plus, so which is equal to f 1 cos omega 1 t plus f 2 cos omega 2 t. So, now by applying the superposition theory, so we know that we can have two periodic response. So, we will have response with two periods. So, one corresponding to this omega 1 and second one corresponding to this omega 2. So, if one plot this phase portrait, that is x versus x dot. So, in this case, so one can obtain two loops. So, by plotting this phase portrait, so one can know, so whether the response is two periodic or is having a single period. Similarly, by putting more number of terms forcing frequency, that is f 3 cos omega 3 t. So, in this case we can obtain a response similar to this. So, that will be, so it will contain 3 frequency. So, we will have a outside loop. So, this is the second loop and this is the third loop. So, in case of these 3 frequency, so if you have 3 period, then we will have these 3. So, in this way one can go on increasing the number of term forcing term, and in case of a linear system also one can obtain. So, in case of the linear system also one can obtain a response with single period, with 2 period or with multi period. Similarly, in case of the nonlinear system also, so for different resonance condition with a single, so in case of a single frequency excitation also, so one can get periodic or 2 periodic or multiple periodic solution. And so, this shows the number of periods increase, that is if we plot this x versus x dot. So, in case of a number of periods increase, so 3 terms with period doubling. So, we have shown this is 4 loops are there, and this response shows a chaotic response. So, we have a number of periods available in this. So, as we are taking a number of periods, but the response becomes chaotic. So, in case of the chaotic response, so one can plot the Poincare section, so which we will study later. So, by taking the Poincare section of the system, so in this phase portrait one can know whether the system is periodic, quasi periodic or chaotic. So, in case of the periodic system, so in phase portrait if one plot, so we will have a single. So, this is x dot versus x. So, we will have a single point. So, in corresponding to 2 periods, so we will have 2 dots, and in case of the chaotic response, if we plot the Poincare, if we plot the Poincare section, then it may fill up the space. So, the whole space will be filled up with these dots. So, this dot represent the Poincare section of the system. So, we will study about the Poincare section later in detail. So, this represent a chaotic solution. So, now we know what we mean by a stable system, unstable system. Also, we have seen some example of different responses, and in these responses also we know what we mean by bifurcation. So, in case of bifurcation, we mean either the stability of the system changes or the number of the response changes. That means, if we have a single branch before, for example, in this case. So, initially we have a single branch, and now so we have 2 branches. So, or we have 3 branches also, we may have 3 branch or 2 branch. So, at this point with increase in this frequency, so we can see that number of branches changes. So, this point is a critical or bifurcation point. So, we will study what are the different type of bifurcation points for the fixed point response, then we will study what are the bifurcation point for periodic response. So, first 3 classes will study about the bifurcation of the fixed point response. So, how to study those bifurcations? So, today class will briefly study, and in case of the multiple solutions, for example, so in this case we have multiple solution. So, in this multiple solution, already I told corresponding to a particular frequency we can know the solutions, or we can find the response from the initial condition. So, different initial condition will lead to different response. So, by plotting those flow from the different initial condition, the plot what we obtain is known as the basin of attraction. So, here this figure shows the basin of attraction of the system. So, in this case it may clearly be noted that this or this correspond to. So, either one can have this negative value or positive value. So, corresponding to A equal to 2, we have one equilibrium position, A equal to 2 and gamma equal to. So, corresponding this value of gamma. Similarly, so this is also equilibrium point, which is A equal to 2, and also one can see that this point, this is also one equilibrium point, but this equilibrium point is unstable. So, this is one unstable equilibrium point, that correspond to the saddle node point, and these are center point. So, by plotting the basin of attraction, so we know what will be the response if one start from one initial condition or initial point. Okay. So, these are a different type of quasi-periodic response, and this is chaotic response. This is a quasi-periodic response because the Poincare response shows a closed curve. And now, we will see what are the different type of solution or equilibrium points, how we will find. Let us first take a first order equation. So, we will start with a first order equation and we will find the response and its stability, and next class we will study about the equilibrium of the higher order system or second order or higher order system. So, today class will study about the first order system. So, let us take, or in general the first order system can be written in this form, that is x dot equal to, x dot will be a function of x and a control parameter m. So, either we can have a autonomous system. So, in case of the autonomous system, so we can write this f x m equal to 0. So, in this case the time terms will not be explicitly present in the system. So, this f x m equal to 0. So, for the fixed point response, we can find the fixed point response by putting this x dot equal to 0 and by solving this equation, that is f x m equal to 0. So, to find the singular point location in the state space where the vector field vanish is called the singular point, and in this case by changing, that is f x m equal to 0. So, if you change this system parameter, that is control parameter m, so we can obtain the response of the system. So, in case of the dynamical system, so either we can have a discrete time system, so in which we will obtain the k plus 1th state from the kth state, and we can have a continuous time system. So, in case of continuous time system, so we can have this non-autonomous system or autonomous system. So, in case of the non-autonomous system, so the time term is explicitly, or this x term depends explicitly on time, and in case of this autonomous system, this time term will not come explicitly in this equation, or we can have this x dot equal to f x m control parameter only, and in case of non-autonomous system we have the equation x dot equal to f x t. So, f is the vector field, m is the control parameter, and x is the state vector. So, for a dynamic system, so we can divide it into discrete time system or continuous time system, and also in discrete time system or in discrete time system we can obtain the k plus 1th state from the kth state. In case of the continuous system, we obtain or we write the equation in this form, that is x dot equal to f x m, where m is the control parameter and this f does not explicitly depend on time. So, now to study the stability, so initially I told you that we can perturb or we can change the state slightly and check whether it is the response is growing or the response is bounded. So, initially by taking, so let x 0 represent, so in our equation x dot equal to f x m. So, let us take that x 0 is the steady state response or equilibrium response, what we obtained by substituting this x dot equal to 0. So, by solving this f x m equal to 0, so the solution what we got, let it is x 0. So, if we obtain the solution to be x 0, then by perturbing it, that means slightly changing its value. So, let us assume that at time slightly different time, that is x t. So, the response becomes x 0 plus y t. So, now this y dot will be equal to f x 0. So, it will be, so now we have to perturb this equation. By perturbing this equation, now we can obtain, so we can substitute this y dot equal to f. So, in place of this, let us our equation. So, we have taken an equation in this form, x dot equal to f x t. Now, we are substituting this equation, this y t is the perturbed part. So, in our original equation, that is x dot equal to f x m. So, now you substitute this x t equal to x 0 plus y t. So, now by differentiating this as x 0 is constant, so this part becomes 0. So, we will have x 0 dot which is constant which is 0. So, we can have this y dot. So, y dot, this x 0 dot is 0. So, plus y dot. So, this will be equal to f. So, for x I will substitute it x 0 plus y, and it will be, let the control parameter becomes m. So, or m 0 I can put the control parameter. So, in this way I can obtain this equation by perturbing this. That means, my equation becomes y dot equal to f x 0 plus y. So, by applying the Taylor series, or I can expand this equation applying Taylor series. So, I can write this y dot equal to f x 0 plus y m 0 plus f, actually I can write this is f x 0 m 0 plus d x f x 0 m 0 into y plus higher order terms. So, as this part, that is our f x 0 m equal to 0 for steady state. So, we obtain this equation y dot, that is the perturbed part, the rate of perturbed part, that is y dot. So, y dot equal to d x f x 0 m y, or I can write this term in matrix form. So, I can write this y dot equal to a y, where A is this matrix which is known as the Jacobian matrix. So, this part is written, this is known as Jacobian matrix. So, in this Jacobian matrix. So, by finding the eigenvalue of the Jacobian matrix, so we can study the stability of the system. So, here is a classification of the bifurcation of the system. So, in case of bifurcation, either we can have this continuous bifurcation or discontinuous bifurcation. So, in case of continuous bifurcation, either it can be static bifurcation or it can be dynamic bifurcation. In case of discontinuous bifurcation, either we can have a dangerous bifurcation or explosive bifurcation. In case of static bifurcation, we can have this saddle node bifurcation, pitchfork or symmetry breaking bifurcation or transcritical bifurcation, and in case of this discontinuous bifurcation, we can have the subcritical bifurcation. So, the subcritical bifurcation may be either subcritical pitchfork or so we will study subcritical pitchfork or subcritical type of hop bifurcation. So, those things we will study later. And so, let us see this equation. For example, let us take this equation and study its bifurcation. So, let x dot equal to f mu x mu, which is equal to mu minus x square. So, in this case, by substituting this x dot equal to 0. So, I have an equation that is mu minus x square equal to 0. So, if mu minus x square equal to 0 or mu minus x 0 square equal to 0. So, I can have this x 0 square equal to mu or x equal to plus minus mu root mu. So, the steady state solution becomes x equal to plus minus mu. So, by changing this control parameter mu, for example, if I will take mu negative. So, if I will take mu negative, then so this will yield imaginary roots or imaginary value. So, which is not possible. So, we will have, so we do not have any response up to this, and then at mu equal to 0. So, this x becomes 0. So, at mu equal to 0, x becomes 0, but for mu greater than 0. So, for mu greater than 0, we have two solutions. So, corresponding to mu equal to 0. So, we have the response equal to 0, but with slight increase in mu. So, one can see that we have two response. So, as the number of the response changes, so this point is a bifurcation point. So, we can have this plus root mu or we can have minus root mu. So, this is the value of x corresponding to different value of mu. So, now we have to see whether this part is stable or unstable. So, to find the stability of the system, so let us take, so for example, in this case our equation is x dot equal to mu minus x square. So, by substituting this x dot equal to 0. So, we have written, so corresponding to x dot equal to 0. So, our equation becomes mu minus x square equal to 0, or we have this x 0 equal to plus minus mu. So, now we have to let us take this x. So, we are perturbing this thing. So, let us put this x equal to x t with time. So, we have started with x 0. So, x 0 plus delta x. So, we have this x t equal to x 0 plus delta x. So, in this equation, if I will substitute this, then I can have this. So, x 0 dot plus delta x dot will be equal to mu minus x 0 plus delta x whole square, or I can write this equation x 0 dot. Already I know that this x 0 dot for steady state, let me write first and then I will tell you this mu minus. So, this by expanding this thing. So, this becomes mu minus x 0 square minus 2 x 0 into delta x plus delta x square, but this x 0 dot corresponding to the equilibrium position x 0 dot. So, x 0 dot minus, so equal to mu minus x 0 square. So, this becomes 0. So, our remaining terms becomes delta x equal to minus 2 x 0 delta x. So, in this case we have neglected the terms as delta x is very small. So, delta x square will be further small. So, we can neglect this thing. So, we obtain this delta x equal to minus 2 x 0 delta x. So, this way one can find this delta x, that is delta x dot equal to minus 2 x 0 delta x. So, our Jacobian matrix becomes, so our Jacobian matrix, so in this case this Jacobian matrix becomes this only. So, that is our A becomes minus 2 x 0. So, we have to find the eigenvalue of the Jacobian matrix. So, to find that thing, so we should write this A minus lambda I or a determinant of A minus lambda I equal to 0, but in this first order equation. So, we can write as this A equal to this. So, minus 2 x 0. So, minus lambda. So, this becomes equal to 0. So, from this, so we obtain our lambda equal to minus 2 x 0. As lambda becomes minus 2 x 0. So, now we have seen that we have two solutions. So, one solution, so this is mu, this is x. So, we have these two solution. So, corresponding to this point, this is x equal to 0. So, now let us take this is root over plus mu. So, this is plus root mu and this becomes root over minus root mu. So, in this case as our eigenvalue, so corresponding to x 0 equal to, so corresponding to x 0 equal to plus root mu. So, let us take mu equal to, so let us take this plus 1 value. So, let this is plus 1. So, our eigenvalue lambda becomes, so already lambda we have written. So, lambda equal to minus 2 x 0 minus 2 x 0. So, this, so corresponding, so if this is 1, that is positive, then this becomes minus 2. So, as lambda becomes minus 2 or negative or the real part of the eigenvalue, in this case we are getting only real. So, as lambda becomes negative, so this response becomes stable. That means, we will have a stable solution here. So, this is a stable solution, and this part, so corresponding to our x equal to minus mu. So, if we will substitute this thing, so in that case our lambda value will be equal to minus, let me take this value equal to minus 1. So, if this is minus 1, so minus of minus 1, this becomes 1. So, our lambda value becomes 1, that is positive. So, this branch, so instead of a stable branch, we should have a unstable branch. So, this is unstable branch. So, this is stable and this branch becomes unstable. Similarly, we can take some other examples also. So, let us take one more example. So, in this case, we will take, let us take one more example in which we will take this, let us take x dot equal to mu x minus x square. So, x dot equal to mu x minus x square. So, in this case for equilibrium point, so x dot becomes 0. So, our mu x minus x square equal to 0. So, for equilibrium position we can find this way. So, if I will take common x, so this becomes mu minus x equal to 0. So, our either x equal to 0 or x equal to mu. So, we have two solution. So, one is x equal to 0 and other one is x equal to mu. So, in this case I can plot the response. So, if I will plot this x versus mu, so I will have two solutions. So, x equal to 0 is one solution. So, this line x equal to 0. So, this line represent x equal to 0 and then we have x equal to mu. So, x equal to mu. So, we have another line. So, this is x equal to mu and this is x equal to 0. So, we have two solution. So, in these two solution, so we should know which part is stable and which part is unstable. So, to find the stability of this thing, so we can potter this equation and write. So, either we can potter this equation or from our previous analysis we have seen this Jacobian matrix can be obtained by finding the first derivative of this part. So, by finding the first derivative, so our derivative becomes, so we obtain this equal to mu minus, so our Jacobian matrix, that is A I can write. So, A becomes mu minus 2 x. So, this becomes mu minus 2 x. So, corresponding to the equilibrium position. So, I can write this is equal to mu minus 2 x 0. So, our lambda will becomes mu minus 2 x 0. So, corresponding to different value of mu. So, for example, if I will take the trivial state, that is x equal to 0. So, in this case lambda equal to, so x equal to 0, let me take. So, if x equal to 0, so this line, so if I will take this line, then lambda becomes mu. So, depending on the positive and negative value of mu, for example, this to this. So, mu for negative mu, so this when mu becomes negative, so this lambda becomes negative, that means this branch, so this to this branch we have a stable solution, and corresponding to this branch, so this to this branch we have unstable solution. And coming back to this x equal to mu, so if I will substitute this equation in this, so lambda becomes, so mu minus 2 mu, so this becomes minus mu. So, that means lambda equal to minus mu. So, for this part, that is when mu equal to negative. So, when for this part, so we have a, so in the previous case this is stable, this is unstable, and now this is for negative value. So, this becomes positive, that is the real part becomes positive. So, that means this is unstable. So, this part is unstable, and corresponding to this, as this becomes positive negative. So, this becomes stable. So, what we have seen, so previously we have two solutions, one stable and one unstable. So, after this point, so this is a critical point after which though the number of the solutions are not changing, but the type of solutions are changing. Here a stable branch become unstable branch, and this unstable branch becomes stable. So, this point is a bifurcation point, and this type of bifurcation or this bifurcation is known as transcritical bifurcation. So, next class we will study more in more detail about the bifurcation of the fixed point response, and we will solve some more examples on this. Thank you.